Good afternoon, ladies and gentlemen. Thank you very much, Mr. Chairman, and thank you for inviting me to attend this very enjoyable conference. I would like to thank the organizers and their team for the excellent job you're doing here. Now, if you speak at the last session of a conference, you are challenged by the fact that everything has already been said, but maybe not by everyone. So I have an introductory slide here which basically has been covered by speakers before. Just to summarize what the message is, storage is an integral part and an enabler of the energy transition to save CO2, and for sector coupling, we have heard that several times. If you look at the different steps of the process here from production to consumption, you see that there is in between smaller circles where it says control and trade. So there's always some management aspect in transferring energy, and there's also an economic part of it. So these two things are two sides of the same coin. Whenever you transfer energy, that has to be technically managed, but as well as economically optimized. This is also a very popular slide that summarizes the different storage applications. We have heard a lot about that from previous speakers. Batteries can provide many of these features. This graph here, which is from the Economics of Battery Energy Storage report from the Rocky Mountains Institute, it distinguishes between transmission, distribution, and behind the meter for the different stakeholders in the system. And what we have also already heard several times is the different applications that are relevant to the grid. What I would like to add here is an example of the ratio of the size of these different markets. Now, if we look, for example, at frequency regulation, primary power control in the German market, the total capacity, the power that has been installed within batteries was about 800 megawatts, and that's about market saturation. But if we look at power balancing or energy balancing in the future system of almost 100% renewables, we will use something in the order of 10 or more gigawatt of battery capacity. So there is a factor of 10 to 20 between these two markets, which means that if we go for a high penetration of renewable energy in the electric system, we will have so many batteries there that we will easily be able to handle the frequency control market aspect of it with a few percent of those batteries. So that's just about what is driving, let's say, battery or storage integration in the longer term. That is more, from our point of view, the energy balancing. Now, batteries are not the only storage technology. As you can see on the bottom left here, batteries cover quite a range. So up goes the discharge time. Batteries you can use from seconds to hours. You have a whole capacity range, which we have seen in some of the projects, from kilowatt hours to several tens of megawatt hours. That makes batteries attractive in combination with the really fast time to realize these projects, as we have seen as well. When it comes to significantly larger amounts of energy and higher power, then there is compressed air energy systems which are being investigated. There's only 2 commercial systems in the world at the moment, one in the US, one in Germany. What is the most common, let's say, grid scale storage technology is, of course, pumped hydro storage, which goes up to the gigawatt scale. In our country, that is also the main aspect. We have about 6.5 gigawatt of pumped hydro capacity with an 85 gigawatt peak over the year. So that's around 10% of the grid peak. But when you go to larger amounts of energy, what is left is then chemical energy carriers, which is hydrogen or synthetic natural gas, methane, produced from power to gas technology. And when I said hydropower is the largest grid storage system, that's 40 gigawatt hours. But the gas storage capacity in the German gas network is 200 terawatt hours. So here you see that by far the largest technical storage systems are those that use chemical energy carriers. There is probably an issue with the coupling technologies. Electrolyzers, when you produce large-scale hydrogen, are coming to the market now. We used to have about 30 megawatt of installed electrolyzer capacity in the country, all funded through public money as well. We now have a new round of public funding schemes where we talk about 200 to 300 megawatt of added capacity, still with public funding. And the scale of the single units is now around 100 megawatt. We just completed a due diligence study for a 100 megawatt project to be realized beginning of this, which will be constructed this year. So we are at the 100 megawatt scale, and you have very significant scaling effects along the scaling of these technologies, but there is limited experience so far with the dynamic operation of these large-scale electrolyzers. So where is the market going? What we see here is the different aspects: small batteries for electric bikes and portables. Storage is a small fraction only, light electric and heavy electric vehicles which use large batteries. So the market is dominated by the electric vehicles. And the growth is also dominated by the electric vehicle market. We see something in the order of 30-something, 32, 33% growth rate for a decade. We are expecting to see that for another decade, which also means that the cost will come down 100 to 250 euros today to 50 to 100 euros, and a capacity of about 100 gigawatt hours will be added. But this is mainly traction batteries for electric cars. We have also briefly heard about the redox flow battery. I would only want to highlight one aspect here. The interesting thing with the redox flow battery is that because you have a separate system for the amount of energy, which is the tanks that store the electrolyte, the liquid electrolyte, versus a conversion system, which is the membrane electrode assembly part, which defines the power output of the system. That means you can scale power and energy independently of each other, which is not the case when you use conventional, let's say, batteries like lead acid or lithium-ion batteries, where you always double capacity and power. So this is an interesting technology, which I think is not utilized to its full potential. On the top right on the picture, you see a development from Fraunhofer, some of my colleagues who have installed a 20 megawatt hour system. In order to optimize the design of a battery system, what we are using is a battery simulation studio. So that is a battery modeling software that allows us to actually look into the aging of the battery system. That means that you can actually look at the whole life cycle of your system and then understand different scenarios, different battery technologies, how they will perform. Often you do not reach calendar lifetime because you have used too many cycles, or the other way around. And this kind of analysis over the life cycle you can do with this very powerful tool, and the precision of this is very, very high. The aging is actually used a lot by the car industry, this aging feature. So my last topic is the pumped hydro storage, which is, as you can see here on these curves, by far the largest energy storage technology, and there are projections from IEA and IRENA where the scaling will go. You can see below the growth of the batteries. At least for the next 2 decades, pumped hydro will be the most important grid storage technology at a global scale. We do not think that we will have 40% growth rates of batteries. It will more be in the 30s at a global scale. We have invented, if you like, a new approach to pumped hydro, which is the STENSI project. You see these spheres on the bottom of the sea. They form a pumped hydro storage system with hollow concrete spheres, and you pump the water out of the sphere against ambient pressure. When you charge the system with electricity, and when you release the water back into the sphere, you generate power with your pump turbine unit. So it's the same principle as a pump storage unit, but it's a new technology. And the commercial scale will be 30 meter diameter spheres with 5 megawatt capacity each, and a 20 megawatt hour energy storage capacity, but there will be many of those at each site. The global resource for this is very large, maybe 1,000 times bigger than what we will ever need in pump hydro storage. I looked up the figures for India. There is about 1 terawatt hour of storage capacity off the coast of India, which is an equivalent of 250 gigawatt of capacity. So someone needs energy storage at a large scale. Why not come and talk to us about this idea? So we have actually installed a small model experiment, just a few pictures on that. So what that means is that you can actually install this also at larger scale in the very same way. We are developing this now as we scale it up at the megawatt range. What you saw as a model was 1 to 10 model scale. 1 to 3 model scale will already be 1 megawatt. And we are currently negotiating that project for funding with the German government. And this is my last slide. There is a whole range of options, a whole range of markets, and you have different energy supply structures. So we recommend that you use a software package to optimize your storage size. I would like to pick up on the body fat gaining experience. I think when you talk about storage, you also have to talk about losing the body fat again, which is not as enjoyable and not as easy as it is gaining it. And you still want to optimize the state of health throughout the lifetime of the system. That's another parallel here, I think. So I believe there is a lot of optimization potential, let's say improve on the economics and find the right technology for the right storage solution. A second project we have realized, which offers also free code that you can use, is a benchmarking exercise of flexibility options with a standardized LCOE method, which then allows you to do a fair and transparent comparison of different use cases. Thank you very much for your attention.
Thank you very much, Dr. Bard, for covering a range of technologies and also highlighting some of the new pumped hydro technologies coming up. In fact, the world is evolving where we are now looking at multiple range of gravity storage technologies, right from concrete blocks to looking at underground pumped hydro facilities. So it's quite exciting field. Thank you.